So in this video, we are going to talk about the convolution theorem. So let's just get into it. So what the convolution theorem says is it relates the convolution to the Laplace transform. So if f and t and g of t are functions, and they have Laplace transforms, capital F of s and capital G of s, then the Laplace transform of the convolution of f and t is just equal to the products of their Laplace transforms. Another way of stating this is that the inverse Laplace transform of a product is equal to the convolution of the original functions. All right. So I am not going to give any sort of argument as to why this is true. I believe there's a small argument if you're really interested in the lecture notes. If not, definitely in the textbooks. So before we go any further, though, let's verify at least that this is true. Okay, so we did this problem as an exercise in the last video, and we got that this was t cubed over 6. Right, so we can take the Laplace transform of the convolution of t with itself is 1/6 times the Laplace transform of t cubed. And remember our power rule, it's the exponent factorial, so in this case 3 factorial divided by s to the exponent plus 1, so 3 plus 1. The 6's cancel, and we're left with 1 over s to the 4th. Okay, so on the other hand, if we compute the Laplace transform of t, power rule again, that's just going to be 1 over s squared. So the product of the Laplace transform of t with itself is 1 over s squared times 1 over s squared. And we see that again, we get s to the 4th. So by seeing that those are the same, we sort of verified, at least for this special case, that the convolution theorem holds. Okay, so there's sort of two different ways to think about what the convolution theorem says, and I sort of hinted at that when I stated it. So the first is we can use the convolution theorem to compute an inverse Laplace transform. So we note that 1 over s squared times s minus 2 is just the product of 1 over s squared and 1 over s minus 2. 1 over s squared is the Laplace transform of t, and 1 over s minus 2 is the Laplace transform of e to the 2t. So what we get then is that this is equal to the convolution of t and e to the 2t. So we see this, and now we're going to have to do an integration by parts. We have w e to the negative 2w divided by negative 2 from w equals 0 to w equals t minus the integral from 0 to t of e to the negative 2w over negative 2. We can compute the integral of that, right? We're just going to divide by negative 2 again. And so we'll get w e to the negative 2w over negative 2 minus e to the negative 2w over 4 from 0 to t. We'll plug in t e to the negative 2t over negative 2 minus e to the negative 2t over 4, and then minus plugging in 0, so 0 e to the 0 over negative 2 minus e to the 0 over 4. And after doing a little bit of simplifying, we'll get our answer is t over negative 2 minus 1/4 plus 1/4 e to the 2t. And that's our final answer. Okay, so note you could compute this a different way by just computing a partial fraction decomposition one thing to sort of note here is if we tried to do that, we would have an a over s squared plus b over s plus c over s minus 2. And from this, we could see that a would need to be negative 1/2, b would have to be negative 1/4, and c would have to be positive 1/4. So, another sort of justification for the convolution theorem, or checking it, right? At least the right stuff shows up. Do another example. So compute an inverse Laplace transform that we tend to see a lot. 1 over s minus a times s minus b. So we note this is the product of the Laplace transform of e to the at and the Laplace transform of e to the bt. And so we get that the inverse Laplace of this thing is the convolution of e to the at with e to the bt. Now, of course, you're welcome to rework that if you want, but I gave it as an exercise in the last class, and we saw that our answer was e to the at over a minus b plus e to the bt over b minus a. So if I want to do a little bit of simplifying, I could write it like that. All right. So on the other hand, we could actually use this to compute convolutions. So this is no expert in this area, but my gut and a couple things that I found tell me that this is more the traditional way, the traditional application of the convolution theorem. It's not necessarily used to compute inverse Laplace transforms. It's more useful to use it to compute convolutions. So we'll use the convolution theorem to compute t to the 4th convolved with t to the 5th. So just before we begin, I just want to note that this is pretty difficult to compute directly. Or it's not really that hard, but it's tedious. Right, I mean, straight from the definition, we have the integral from 0 to t, w to the 4th power times t minus w to the 5th power dw. So we would have to expand a 5th power. We could switch the order, but then we're still expanding a 4th power. So it's kind of a lot of work. However, if we use the convolution theorem, we know what the Laplace transform is going to be. It's just the product of the Laplace transforms of t to the fourth and t to the fifth. So remembering our power rule, we have 4 factorial over s to the fifth times 5 factorial over s to the sixth. Or 4 factorial times 5 factorial over s to the 11th. All right. So then we get that the convolution of t to the fourth and t to the fifth is the inverse Laplace transform of 4 factorial over 5 factorial over s to the 11th. Well, I have an s to the 11th, so that should correspond to a 10th power. So I'll pull out the constants inside, and then I'll multiply by 10 factorial and divide by it. So this then is just going to be t to the 10th. And now I can do, remember what the factorial is, right? So 10 factorial is 10 times 9 times 8 times 7, all the way down to 2 times 1. So it's the product of the numbers 1 through 10. So to sort of simplify things a little, I can cancel this 5 factorial with the first 5 numbers of the 10 factorial. So I'm going to get 4 factorial all over 6 times 7 times 8 times 9 times 10. And let's see, well, I can cancel that 2 and the 3 with that 6, and I can cancel that 4 and leaving me with a 2. So I get 7 times 2 times 9 times 10, and so I can get t to the 10th over 1,260. And so my answer for t to the 4th, the convolution of that with t to the 5th, is t to the 10th over 1,260. I'll do one more example. Or actually, let's make this an exercise. So use the convolution theorem to compute the convolution of t squared and e to the t. All right, so give it a minute, work on it, pause here, and okay, let's go over the answers. So I'll work this one through just because it's a good example, and you know, more stuff of that. So, right, we don't want to compute this directly. We use the fact that this is equal to the Laplace transform of t squared and the Laplace transform of e to the t. So that's 1, or not 1, but 2 over s cubed times 1 over s minus 1. So to compute the inverse Laplace transform, which is what we need to do, we have to do partial fraction decomposition. And this partial fraction decomposition, you know, it's kind of annoying. It's going to have 4 terms, but they're pretty simple terms. And if we wanted to do the convolution, we would have to do a double integration by parts. So, you know, we have to do some partial fractions, but we're avoiding a double integration by parts. So I think that that's definitely worth it. So 2 over s cubed, s minus 1 equals a over s cubed plus b over s squared plus c over s plus d over s minus 1. So 2 equals a times s minus 1 plus bs times s minus 1 plus c s squared times s minus 1, and then plus d s cubed. So if we plug in s equals, let's say 0, then we get that 2 is equal to negative a. So a is equal to negative 2. If we plug in a1, right, we'll get 2, that's 0, that's 0, that's 0 equals d times 1 cubed. So d equals 2. And then we're sort of out of things to make everything cancelable. We can plug in a negative 1. 2 equals negative 2 times negative 1 times 1, so that's negative 2. And so we'll get 4 minus 2b minus 2c minus 2 equals 2. So if we simplify this a bit, we get b plus c equals 0. And lastly, I'll plug in 2. So that a is negative 2, so that's just going to be negative 2 plus 2b plus 4c, and then plus 8 times 2, so plus 16. So let's see, negative or positive 14, subtract that, so negative 12 equals 2b plus 4c. Negative 6 equals b plus 2c. This says b equals negative c. So c equals negative 6 and b equals positive 6. Okay, so to go back, I have negative 2 over s cubed plus b, which is 6 over s squared, minus 6 over s, and then plus 2 over s minus 1. So if we compute the inverse Laplace transform, we see that t squared convolved with e to the t is equal to 2e to the t minus t cubed plus 3t, then plus 6t and minus 6. Right. And we will end it there.